Okay, guys, welcome back to day 4 of gravitation. In yesterday's class, I introduced gravitational field and how to talk about gravitational fields and all. And I said I asked you to, check the fields because from the different bodies. But anyway, I'll deal with it, or I'll discuss them today. Okay. In yesterday's class, I dealt with one problem where the gravitational field because of some rod at some point, which is at a faraway point. What we did is at a distance dr, we took a small mass dm. We wrote the field because of this small mass, which is de, and then we integrated it. The whole thing was integrated from one end to another, and from which end to which end? From this end A to this end B, we integrated the whole length, and we got the field because of this rod. Now, what if the rod is not like this? What if the rod is like this? Like a problem that is given in H.C. Verma. He asked the field because of this rod about this point. How are you going to do this? Again, this distance is d. Okay. Now, it will be a long process for sure. At a distance x, I take a small element, dx element. And because of this, I am going to write the field. I will get dE. If you want me to write that, I'll write the value, okay? Like dE value. Gravitational constant into g dm by the distance, this distance, which is nothing but root or d square plus x square whole square. Clearly observe, because this is a right angle triangle. So from that, I wrote the distance. Now I have to mention the dm also. So to be clear, dE equals to g m by l into dx. We all know how to write dm by now. We should be knowing it by now. If you don't, it's not acceptable. D square x square, square root and square, so they're balanced. So you'll get a value like this. Now you cannot integrate this. The problem is, if you integrate, you have to integrate from a value of x. The value of x varying from minus L by 2 to plus L by 2. So those will be the limits. But the problem is, if you integrate it, you're integrating all the dE values, like which are in different directions. And it's as if you're adding multiple vectors, v1, v2, v3, v4, v5, by not considering the directions. You cannot directly add the magnitudes of v1 and v2 and v3 and v4 and say that is the resultant. No, this is not how you simply add the magnification, the magnitude. You cannot directly add the magnitudes. So if only you directly integrate this, you're doing the same thing. You're simply adding all the magnitudes. You shouldn't do that. What you need to do is, obviously, I'm starting again. Clearly watch. I am taking the rod at some point, and at a distance x, a small element dx. Because of that, the field is dE, which came as how much? G m by L into dx. I remember that from the previous page only. Root or d square plus x square. So this is d. So this distance is nothing but root or d square plus x square. This is value of d. Now I cannot directly integrate it, but I can do one thing. I can take the component of it along this line, which is d cos theta. Now all the components are in the same direction. Now I can integrate this value. Yeah, I hope you're getting my point. Like if you're not getting my point, clearly try to, don't hesitate to ask. I'm taking the component, which is g, the same value, g m by L dx, d square plus x square cos theta. And I'm going to write, I'm sorry about this notification. And I'm going to write g into m by L dx by d square plus x square. The cos theta value from this right angle triangle, cos theta is nothing but d by root over d square plus x square. So d by root over d square plus x square. So g m by L into d into dx, I just replace these two, by root over, d square plus x square whole power 3 by 2. This is dE cos theta. Now guys, this you can definitely integrate because all the dE cos thetas are horizontal only. Since all the dE cos thetas are horizontal only, you don't really have to worry about it. Now this value you can integrate it from minus L by 2 to plus L by 2. How to integrate this value is not my job. I'm not teaching you. Sharath, what is it?
Excuse me, sir, while we write d square plus x square, sir, we'll be specifying the direction, right? So like net, the net magnitude will be different, right?
But all the directions are horizontal only, right? So that is why I can integrate. That's the, I mean, you are you asking me a question or are you suggesting something?
So questions, sir, like
Like
when we
what's,
take d square plus x square, sir, we'll get the distance between the mass and the point, right, sir?
yeah,
So the only thing which we'll have to specify is the direction. So we won't need that cos theta and etc. Right? Like
but like you said, if you have, then you write the integral with a vector. Like mention this dr cap and then integrate. But your mathematics standards are not good enough to integrate with a vector. I don't think so. Okay.
even
So this
I
part
thought
you
of the same
cannot
thing,
do. So
sir.
that is why we do this. We only take a component and we do it. Even in that case also they do the same thing, but in a different, it looks in a different manner, but yeah. So I think this is clear. Aniket, what is your doubt?
Yes, sir.
So after doing this integration, how should we get the actual D?
Actual d value must be given. D is fixed. They have to give d value.
Not D, sir, sorry, the E.
No, you will get the integration of this thing, which is nothing but this value is nothing but ex, field in the x horizontal direction. I will talk
Remaining
about
directions we don't need, sir.
I will talk about EY. Wait, I will talk about EY later. But this value is EX. So the whole value that you get out of this thing is nothing but EX, which is actually the thing that is given in your textbooks. Integration of this thing, it's quite easy. It's not really that difficult. G m by L into D integral dx by D square plus x square per 3 by 2. If only you go through your old integration formulas, you will directly see a formula for this. There's a direct formula for this. You do
Okay,
that,
sir.
then you put in the limits minus L by 2 to plus L by 2. Now you get EX only. The reason why I'm elaborating this question is it is helpful for the other questions. Okay. What about other values? Like, yeah, it's good that I took some component. It's good that I took some component DE cos theta. That is so cool. But what about DE sin theta? What happened to DE sin theta? You can write dE sin theta also. You can integrate dE sin theta also, but I'm pretty sure when you integrate it, you'll get a value that is 0. Can somebody tell me why?
So for your question's answer,
Yeah,
this because if I take one mirror image of this DE, sir, the D
exactly.
sin
The
theta will
point
cancel the
is,
above one.
like, because of this mass, you're writing dE, right? Because
Yeah,
of this
take the
mass, you're writing
mirror, sir.
E. Now, because of this mass, you will get another dE sin theta later in the integration. These two will balance each other. So you don't have to worry about EY. EY is already 0. All you need to do is calculate the EX value, which we did here, right here.
Sir, I have one doubt also, sir.
My pen is
Like,
not working. Yeah, what is it?
so instead of integrating from minus L by 2 to plus L by 2, can't I integrate it from 0 to L by 2 and the final solution into 2?
Right. 0 to L by 2 and integrate, like, yeah, you can multiply it by 2 and you'll get the answer, same answer. Yes, for sure.
Yes, sir.
Yeah. Neeti and Preeti, can you raise your hand? And I don't understand which part you didn't understand. Aniket, what is it again?
So instead of going from this middle, if we do like from 0 to L,
then you have to take a different stand. Okay, like the reason why I took 0 to L by 2 and like minus L by 2 to L by 2 is I started X, I measured X from the middle. You see that?
yes, sir.
And to do the same thing that you asked, I have to take the rod like this and I have to measure X from one end. Then I have to take 0 to L by 2. If you take the problem as in the first case and you write the limits as 0 to L by 2, you are clearly meaning that there is no rod in the lower half. You're clearly telling that the rod started here at the bottom, and you're saying the rod is extended up to L. Sorry, like if you write integral 0 to L, you're saying the rod is extended up to L. That's not the case, right?
Yes, sir.
Yeah, so that is the reason why there's a reason why we're doing this. Like when you took the rod, guys, my pencil is not working for some reason. Okay, it's the issue with the app, not the pencil. So since I took from the middle, I measured x from the middle. That is why I have to write minus L by 2 to plus L by 2. Like Aditya, you can do that, but this is a professional way to do it. Now, Neeti and Preeti, what's your dot?
Sir, can you scroll the page?
Yeah. I did more. You want more?
Yes, sir. Yes, sir.
Okay.
Sir, there you write now, sir, into
I can't
d
hear
by...
your voice. I can't hear your voice.
Sir, can you hear me now?
Yeah.
So you wrote like the first step, d into d by under root d square plus
Yeah.
at that step, sir. How
Like
do you
this value is nothing but cos theta. From this triangle, check this, cos theta is nothing but d by root, or like, right? This is x, this is z, this is x, and this is theta, this is do square plus x square. What do you get when you write
Yes.
cos theta?
Yes, understood, sir.
Yeah, that is why I got cos theta. But yeah, it is a bit complicated to look at all these equations. But guys, nobody is going to ask you these formulas. You just need to understand the method, how we approach the problem. Okay, clearly follow the method only.
Excuse me, sir.
Yeah, Aniket, tell me.
So if we take like that, how I said from 0 to L, then the y component will be there.
Yeah, obviously. Like if only the rod was given like this and the point was given here, not on the perpendicular bisector, but somewhere around here. Yes, in this case, if you have to measure x and this element is dx and this is dE. Yes, when you put the limits as 0 to L, it's not just dE cos theta, there will be dE sin theta also. That's a good question. So there will be dE sin theta component also in that case.
Sir, and one more doubt, sir.
Yeah.
So what if it is at some angle, the rod?
You do it. Like the rod is here and the point is here. Is that okay for you?
Yes, sir.
No. So what I do is I take this as the base level only. I measure x from this point only to some element dx. I write the field dE since this distance is d the same way. But when I put in the limits, what do I do? From A to B. They have to mention all the values from the A value, B value. They must at least give some angles, right? From the angles, you can find the values of A and B. And when you put in the limits, you simply put A to B. Do you get it, Aniket?
Thank you, sir. Yes, sir. That's a simple method, sir.
Yeah. So it's quite easy. Like this method, you must know this method. So that's why I'm giving you. So guys, am I saying electric field again? If I'm saying electric field, ignore, it is gravitational field only. Okay. Now, let us talk about a much simpler question now that I mentioned yesterday. A semicircular ring. It's a full ring. If it is a full ring, there is no question that you need to ask. It's 0 at the center because it's a null point. All the masses are attracting and it makes it a null point if it's a full ring. But if it's a semicircular ring, instead of measuring with length, I choose to measure it with angle. So we can take the angle from any point. It's your call. Let's take from this level at an angle theta. There is a small element d theta, like Aditya suggested, we do this. So this element, this is a small element whose length is r d theta. Why did I use the blue ink? Wait a second. So at an angle theta, d theta, so this element is r d theta. We have a field in this direction which is dE. Okay, you can write dE. dE is very easy to write. G dm by the distance is fixed this time. We have a quite an advantage here. In the previous situations, so in the previous situations, the distance was varying. Like the distance was how much here in this problem? Like it is root over d square plus x square. The distance was difficult to mention every time. Root over d square plus x square. Now the distance is quite easy to write. The distance is simply r. So g dm. So g dm by r square. That's all. But g, the value of dm is important here, because for pi r length, that is the length of a semicircular ring. For pi r length, the mass is m. For pi r length, the mass is m. So for r d theta length, the mass is dm. So if I cross multiply it, I get a dm equals to m by, wait a second, m by pi r into r d theta. So r cancel. So dm equals to m by pi into d theta. I put this dm there in this place. So d equals to m by pi into d theta by r square. So this is the value of dE, and we can integrate. Now, can we integrate? No, we cannot. Why shouldn't we integrate? Anybody? Raise your hands and say it. Why shouldn't we integrate it directly? Yeah, why shouldn't
So
we?
you haven't specified the direction, sir.
Exactly.
Yes, it's the
Because
same thing, sir. Direction
if
is
only I take DE, the DEs will be in all the directions. I cannot do this. So I need to be a good boy, and the element is here. DM mass element is here, whose field DE, whose value is just something that we just found, which is how much? This much. So G m by pi into r d theta by r square. Sorry, m by pi into only, there is no r square. This is d, but I cannot directly integrate d. What I have to do is I take d cos theta. I take d cos theta. So d cos theta will be equals to gm by pi d theta r square into cos theta. So if I have to integrate it, all of them are constant, gm by pi r square. Only cos theta, d theta are the variables. Integrating on this side also, this will simply gives us ex value, because we're only talking about ex. Can somebody tell me the limits? Can somebody give me the limits? Aniket, I'm giving you the chance. What are the limits?
So 0 to pi.
No, if you do that, like again, be careful. Clearly observe where we started measuring it from. We started measuring it from this, like this is the base limit. So if you're talking about 0, this is 0, this is pi. So
So
you're
minus pi
saying
by
as
2
if the
to pi
ring
by
is
2.
like this. You getting my point?
Yes, sir.
But the ring is not like this. The angle started from minus pi by 2 to
Pi by 2.
exactly minus pi by 2 to plus pi by 2. So when I integrate this value, I have to put the limits as minus pi by 2 to plus pi by 2. Cos theta integration everyone can do. Chetan has a doubt. Chetan, what is it?
Sir, we can also say that it started from plus pi by 2 and ended at minus pi by 2.
But you always put the lower limit first and the upper limit later, kada? I hope you get it.
Excuse me, sir.
Yeah.
So can we add the cos theta component and sin theta component in the end?
You write cos theta component and write it as I cap, and then write the sin theta component and put a j cap. It's fine.
We can't take resultant, sir.
Yeah, if somebody is asking you the magnitude, you can take the resultant. Don't directly add the magnitudes. You have to write root over ex component.
Okay, sir.
Yeah, like somebody is asking you the resultant, you can write it like this: ex I cap plus ey j cap, or you can simply give the magnitude saying ex square plus ey square. Now, can somebody tell me what is the value of ey in this case? Aniket, why you guys are going in mute every time?
So 0 is EY,
So
sir.
0, sir.
It
Just
is
like the
zero
previous
because
one.
it is like this. The body is what do you say? Symmetric.
Symmetric.
So if I take a body here, I'll have another body here. Both the vertical components balance each other. Both the horizontal components are adding. So that is why you're only getting EX. The EY is becoming 0.
Sir, one
Okay, guys?
small doubt.
Yeah, tell me.
So this after adding both the vectors, the cos theta and sin theta one, will we get the same value as that if we didn't take any components?
What?
So you told the wrong way, right, sir, without taking this cos theta?
But vectorial, you are integrating vectorially.
Yes, sir. And then
But
summing
there
it
is
up.
no way that you can do it. Like you cannot do integration with vectors right now.
Okay, sir.
So you cannot do that. And even though people who do that actually do it like this only. That way is no, there is no other way. It's as if you're going this way and you want to go this way. There's only one way. You can have to go this way and I'll simply redirect you to this path only. So there's no other way to do it.
Yes, sir.
Okay. So that is a value for a semicircular ring, guys. I hope you're getting the method. I don't need you to remember the formulas right now because by the end of this week, we'll all develop a table of all the electric fields from the table itself. Like those values are
Sir,
more
it's
than
gravitational fields.
okay, more those gravitational field values are uh, totally fine. I mean, like you can happily live with those values. The gravitational field values for specific bodies, I will give you at the end of this week. You can happily go with that, but I just want you guys to understand these methods so that you can, when you approach some new problems, you will be ready to do it. Okay. Let us look at a full ring only. Next body I'm talking about a full ring only, but not at the center. Everyone knows the center is a null point, so there is no point in discussing the center. But now I'm talking about some random point. At this random point, how would we do it?
So can I say?
Sir,
Yeah,
here the y component is 0, right? Just like
obviously
the
that's a
previous
good
ones.
thing. Ey is already 0 because if you take one dm mass here, another dm mass here, both the fields will have ey, they will balance each other and ey will simply become 0. But ex's, all the horizontal components will add each other. So
Sir, we'll have to do it like the rod case, right?
no, you don't. This is
Sir, like how we do for that semicircular ring, but we have to just extend some distance, sir.
no, it's very simple compared to semicircular ring. In
Yes,
semicircular
actually.
ring, the DE angle is changing. Did you observe that
The angle won't change here.
in a semicircular ring, the DE value is like this, and then like this, and then like this, and then like this, right? But in this situation,
It forms a
the
cone.
whole ring is as if again my only kind of body. So like only consider the edges of this body, okay? If I'm considering a point like this, all the angles to this point, they're all same, right? So they're not even at different angles. So the integration gets a lot more easier in this case, okay? So I'm taking some random mass, I'm writing some field dE. I will write dE cos theta. You will clearly see the answer will come so easily. Let's observe that, okay? The r, this distance is d, so this right angle distance is root over r square plus d square. So let's write the field g into dm by root over r square plus d square whole square, that is de. But we are not happy with de here, we want de cos theta. So g dm by root over r square plus d square whole square into cos theta. Now the cos theta value g dm root over r square plus d square whole square by d into root over r square plus d square. Now it looks like the similar problem in the previous problem, but there's only one difference. In the previous problem, we used to have an x in the value, which is a variable. Here we don't have an x. We don't even have an x. All we have is all the constants except for this is a variable. So I take gd by r square plus d square whole power 3 by 2 into dm. dm is the only variable. When I integrate it, I can directly integrate it from 0 to m. That's it. That's the answer. This is the answer for a semicircle, sorry, a full ring. Guys, this is a value that you have to remember. In the future, I'll make you remember it. Like out of the table that we get, the final EX value that we get is this, okay, which is nothing but GD by root over R square plus D square whole power 3/2 into M. That is with a circular ring on a point. This is called as an axial point, guys. Remember this thing. It's called an axial point. And somebody has mentioned EY. The value of EY will be 0. I don't understand why people are sending messages like 0, 0. Are you talking about, I don't know. Aniket, what is it?
So axial because it passes through the axis.
Exactly. Yeah, that is the reason why. That is the reason. Oh, okay. What did I do? That is the reason why it is called as an axial point. This is a point on the axis. We have a semicircle, so we have a circular ring, and the point is on the axis. So that is why it is called as an axial point. And we just found the value of EX on that point. We all know that EY is already 0. So remember, we will remember these values. Don't worry. But for now, all you need to do is just simply understand the process. That's all. Okay. If we are done with the semicircular ring, let's look at a tough one this time. Sorry, a circular disc. Did I say semicircular ring? It's a ring. I'm sorry. A simple ring. Now we are talking about a disc. On a disc on an axial point. Anybody's idea how we do it? On an axial point, I want the field at some random point.
So we do it like the ring, but we'll have to consider theta, sir. Like we'll have to take the ring one, then we'll have to consider theta and integrate it.
Like all you need to do is take a ring R and thickness dr, write the field because of the ring Ex because of the ring you write. So let's call it as Dex. And then you integrate, you will get integrated from what? 0 to capital R. You write the whole field. You don't find this thing anywhere, okay? Like in the problems, you will never find the disk. I'm just giving you the method. You will never find this person. If you find it, you're just unlucky. All you need to do is write the field because of just the disk, sorry, just the ring, because we already know the formula of the ring. So you write the field because of the ring here at this point, and then you integrate it from 0 to R. You're actually talking about a disk. That's it. We're done with a complicated body. Let us look at a very simple body, but it looks so complicated. It's looks so complicated, but it's one of the most easiest bodies. Hollow sphere. One of the most easiest bodies, but it looks so complicated. So let's jump into it. A hollow sphere. Every time I draw a hollow sphere, I put some lines like this so that it conveys it's a hollow sphere, okay? It's not a ring, it's a hollow sphere. It's a center. And we are talking about some random point. And we are talking about some random point. And now, the field because of this point. Now, to find the field at this point, some random point P, what's the best approach? Like to look at this, what's the best approach? Aditya and Sharath.
Sir, we'll have to consider multiple rings at different distances.
Exactly. So
Yes,
this is a sphere. I consider this whole sphere as a combination of a lot of rings. It's a combination of a lot of rings, as if the rings go like this. It's a ring, and there's another ring, and there's another ring, and there's another ring. So all these little rings, we are going to take all those little rings. In fact, we're going to take one single ring and write the field because of that one single ring. We already know the formula for one single ring. We integrate it. This looks like hell, but in the end, you will find the sweetest, simplest answers that you've ever seen. In the entire gravitational topic, this is the most simplest formula. Okay, I can even give you the answers because you look terrified already. I mean, you might be terrified already. The answer simply comes like gm by r square. simply like a point mass. Then we do it for inside the sphere. The value comes as 0. So the answers are this simple. So please bear with me throughout this entire process. Do you want me to discuss or do you want me to skip it?
Sir, one thing I want to say, sir.
Yeah.
In the starting of the lecture, you told like all circular objects can be considered as a point mass. So we might find some same formulas for it.
That's for sphere, right?
Now, even for the hollow sphere also you can do it. But we don't just do it, right? Like I have to mathematically prove it. In the beginning, I also said we can do it mathematically. We can prove it mathematically, and this is the
Yes,
proof.
sir.
Okay. Aditya, sorry, Aniket. What?
Sir, can you prove it with varying density also, the same thing?
Oh, yeah, we can prove it. So I hope you can see the ring that I just considered on the sphere, on the surface of a sphere at some point. We are going to write the field because of this ring at this point. First, that is the first thing that we are going to do. Clearly observe the whole process. This is going to take some toll on your heads, your brains. They might hurt. But in the end, believe me, the answers are very simple. Now, the whole distance is given as d. Let us call the whole distance is given as d. Now, the distance from the ring is how much? This is the distance that we need. How much is this distance? If you clearly observe, this is also r. So this will be r cos theta. So I can say this is d minus r cos theta. You're getting my point. This is r cos theta. This is d minus r cos theta. The whole thing is d. And this is r sin theta. So I'm going to take this ring aside to another point. I'm going to take that ring aside separately. So now I have a ring. Now I have a ring whose radius is r sin theta, whose distance from the point is r cos theta minus d, and I want the field because of that ring. Okay, and the mass of the ring is not also simple. The mass of the ring is dm.
Sir, it's d minus r cos theta, sir, not r
What?
cos theta minus d. It should be d minus r
Oh,
cos theta.
I'm sorry about it. The distance must be d minus r cos theta. This is where we can go wrong. That could have been terribly gone wrong. Now we know the formula for a ring. All you need to do is apply the formula for a ring. Where is the formula for a ring? Can somebody find it for me? Yeah, this is the formula for a ring. Can somebody remember this is gd by root over r square plus d square into m, right? So yeah, I remembered it. G, the distance is d minus r cos theta into dm by root over r sin theta whole square plus r d minus r cos theta whole square. In the place of d, I'm
All
putting
cubes.
that. Yeah.
So we'll have to put a cube in the denominator, sir.
Oh, there's a cube. Oh, thank God, man. I'll just put a power 3 by 2. That is simpler. So power 3 by 2. Okay, now it is not over. It might seem like it is over, but this takes forever. Don't worry. Aniket, what happened?
So that dm, can we take like 2 pi r into dm?
No. That's what we're going to do right now. I'm going to write this whole thing again here. G into dm d minus r cos theta by, if I expand this thing, you get a very, though I won't expand it. Okay, I won't solve the whole thing. If I solve the whole thing, the day will be over because of this. Whole power 3 by 2. Okay. Now, guys, the dm value is also not supposed to be put here. The dm, you can't just leave it as dm. Let's go back to the original thing. The surface area of a hollow sphere is 4 pi r square. For that, the mass is m. What is the area of the ring? The area of the ring is nothing but the circumference, which is 2 pi r, which is 2 pi r sin theta. This is the whole length of the ring. Into the thickness is r d theta. Did you see that? Do you remember r d theta is the thickness? So This is the area of the ring, the length of the ring into the thickness of the ring. So 2 pi r sine theta into r d theta, the mass is dm. So you cross multiply it, you get the value of dm here, you put it here. Now do you feel like you are scientists already? I'm not going to continue the method. And then when you integrate it from this side to this side, which is Aniket, now it is your turn, like the angle from 0 to pi, which means I'm integrating all the rings. I hope you're getting my point. Now, I mean, if I'm integrating from 0 to pi, I'm integrating all the rings. I'm covering all the rings, which covers the entire sphere for me. And the answer comes because of this hollow sphere whose mass is capital M at a distance d. The answer comes as gm by d square. That's it. It looks as this complicated, but as integrated, everything gets cancelled, everything gets simplified, and in the end, you'll get a simple answer like gm by d square. Just like a point mass, you'll get a hollow sphere. Now it's not over. This is not over. Since you people asked, you have to suffer. We are talking about an inside point now. We're talking about an inside point now. Does anyone feel like murdering me right now? Can you kill me? So the same thing, theta, r, d, theta, everything is same, except I take an interior point. Everything will be same, except the distance from the ring changes. The only thing that changes is the distance from the ring. Since we're talking about this is a distance d, like from the center, the distance is d, and there is r cos theta. So from the ring, it is at a distance d plus r cos theta. And just because of this plus, the whole integration changes and you'll end up with a value that is 0. So guys, forget everything that I just said. If you don't understand it, it's totally fine as long as you're concerned about a mains problem. Even in advanced also, nobody's going to ask you to prove it. In the end, what you need to remember is the gravitational field outside a hollow sphere, the gravitational field outside a hollow sphere at any point whose distance is d from the center. Guys, remember, please don't measure it from the surface. From the center d, the value is gm by d square. And the inside, the gravitational field inside is 0. So there are no gravitational field inside at all. So in a hollow sphere, there are no gravitational fields. So if you are sitting inside a hollow planet, a planet which is hollow, you will feel weightless. Remember this point. Inside a hollow planet, you will feel weightless. Aniket, what is it?
Sir, what if we have to measure from the surface or like some random point inside the sphere?
I didn't understand.
So like without taking along that axis.
Without taking along that axis, where else can you place a point?
So anywhere else, sir?
No, where else can you take a point for a hollow sphere? You want to take it here?
Yes, sir.
You stupid, this is an axis also.
Oh, okay, sir.
Yeah. Aniket, how old are you, Aniket? Please. How old are you?
16, sir. So like, for example, if that is considered
How old
like
are you again?
16, sir.
16. Yeah. Are you sure that's not your IQ?
Not that, sir. Like, if it is considered like some x-axis, then, sir, some third axis.
No. Sumantra is asking, is it similar to a vacuum chamber? No, this has nothing to do with vacuum. Vacuum is when the whole space is, like the whole gas is removed. There can be air inside it. Okay, there can be air inside it. It's not going to affect it. But the gravitational field, because of the mass inside the whole hollow planet, will be 0. There won't be any gravitational field. You can put any body anywhere, it won't move. And just like this stupid person asked, what if it's not an axis? There is no such thing as an axis for a hollow sphere. Everything is axis. So if you want this point, you take this distance. If you want this point, you take this distance. Okay. So that is it for a hollow sphere, guys. Please remember these values. That's all. If you don't understand it, if you understand it, it's more than good. Sharath is asking, do we have any celestial bodies which are hollow bodies? Not that I know of. No, I don't think there are any bodies which are hollow. No, I don't think so. Okay. Let's talk about a solid sphere. Let's talk about a solid sphere. Now, you might already be worried that for a hollow sphere, we have to crack your brains open to find the answers. But for a solid sphere, it's much easier. Can somebody give me the answer, which is very simple? Sumantraj, what is it?
In this for the solid sphere, we can just integrate for infinite disks, right? Sir?
I can't hear your voice in first place.
Sir, are you able to hear me now?
Yeah.
Sir, we can just integrate the infinite number of disks by taking like
disk. You want to multiply, like integrate the disk. Okay. Does anyone have a better idea, Sharath?
Even I was about to say the same.
Disk, that is very painful. Why do you have to do it with a disk?
So hollow spheres, many hollow spheres.
Exactly. You simply take a hollow sphere. But the best point about this problem is so simple. Let's check this. Let us say the hollow sphere's mass is dm. As the radius of the hollow sphere is changing, one thing is not changing. No matter which hollow sphere, even throughout the solid sphere, no matter which hollow sphere are considering, for all the hollow spheres, the distance is d only. So for all the points, the field is g dm by d square only. There are no variables. All you have to do is integrate g by d square, integral dm, 0 to m. The answer is gm by d square. That's it. I hope you get the point clearly. Like, because all the hollow spheres, the distance is d only from the center, no matter which hollow sphere you're considering. It's as if you're writing all the fields because of all the hollow spheres, which is g dm. It's like g small m1 by d square plus g small m2 by d square. It's like g small m3. All m1, m2, m3 are the masses of hollow spheres, which are piling on to make this a solid sphere. So for a solid sphere, outside a point, the answer is still the same thing, gm by d square. There is no change at all. Aniket, what is it?
Excuse me, sir. So instead of hollow sphere, suppose we take the ring. Can we still do it?
A ring? You cannot take a ring. If you take a ring and integrate, you're creating a hollow sphere. You want to take a disk.
Okay, sir.
Such a painful process. It's like, no, I don't understand why would you want to do that? It's very simple. Like every hollow sphere, it is at a distance d. So it's as if I'm adding all the little hollow spheres of masses m1, m2, m3. All the fields are gm by d square, gm by d square. If I take that common out, g by d square of masses of all the hollow spheres m1 plus m2 plus m3 and all, what I'm getting in the end is gm by d square. So for a hollow sphere,
if it is inside the sphere,
that's where we are getting. So for a solid sphere, we just found out the answer. For an outside point, the answer is simply gm by d square. But for this is outside. Can somebody be a little clever and give an answer for an inside point? The radius is r. I want the field at an inside point. Can anybody has any idea? This is a very interesting. I mean, like, if you can find an idea to this, I think you will crack the exam. Nobody? Neeti and Preeti are saying it's 0. No, you can't guess it. Give me a method. Sharath, what is it?
Sir, I have this approach, sir. What we are supposed to do is first we are supposed to take the right hand side and integrate separately, sir. Then the left hand side and integrate separately. And then subtract one from other.
No. Listen. I am splitting this solid sphere into two parts. One is inside part. The other is outside part. Okay. One is inside part and the other is outside part. You clearly observe the inside part is a smaller sphere with a radius d. The outer sphere is a hollow sphere. The outer sphere is a hollow sphere. So because of the outer sphere, the field here is 0. So for a solid sphere only, you're taking a solid sphere, you're talking about an inside point. You're talking about an inside point. All the red part is not even creating any field. All you need to do is you have to find the field due to the smaller sphere, and that's all. That's it. That's the answer. For this smaller sphere, the field. All I need to do is G m of the smaller sphere. Let us call it as blue sphere. M of the blue part by d square. How do you find the mass of the smaller sphere? Anybody?
You'll have to take the density.
Exactly. Like because the bigger sphere, the overall sphere's mass 4/3 pi r cube has a mass capital M. The smaller sphere's volume is 4/3 pi d cube. It has a small m blue. I'm going to call it as m blue. Okay, so if I take ratios, m blue by capital M equals to d cube by r cube. So all I want is only m cube. So I'm going to put it here. So the field equals to G into m blue is nothing but d cube. This is d cube. D cube by r cube into capital M by d square. This cancels cube. So I get G d by r cube into m. You can simply put it as gm by r cube into d. You see the simpler process now. Sharath, you get it?
Yes, sir.
Okay.
Sir,
Sir,
I
I
didn't
have a
understand
small.
why we should not consider the red part.
Because the red part is a hollow sphere, right? And the hollow spheres don't create the fields inside. Do you get it, Aniket?
No, sir.
Which point are we talking about? You're talking about this point, right?
Yes, sir.
Now, the red part, for the red part, this point is an inside point. Oh, no?
Yes, sir.
So for the red part, the green point is an inside point for a hollow sphere. For a hollow sphere, it cannot create any field for inside point. Do you remember that?
Okay, sir.
So that's why the red part is not creating any field here. Only the blue part is creating. So I simply found the field because of the blue part, but I had to find the mass of the blue part. So I took the densities, made the adjustments, and found the answer. Guys, even though you didn't understand any of this part, please try to remember. I'm simplifying the answers again.
So what about hemispheres?
It's very complicated for hemisphere to find. It's very complicated.
Sir, instead of this hollow sphere, if we had taken anything else, it would again we have to calculate, right?
Yeah, it's very difficult. Yeah. We are only dealing with the bodies which are easy to find and that are naturally occurring out there. Like most of the planets are spherical, right? So that's why we considering the basics of it. Okay.
So once can you discuss variable density also in this?
Not today, but in this topic at some point we will discuss. Okay.
Okay, sir.
So where was I? For a solid sphere, outside point field is gm by d square only. Inside point, the field is gm by r cube into d. Try to remember these four values, not four. These four values are important for a hollow sphere, inside, outside, for a solid sphere, inside and outside. And along with these, simply take a point mass. There is no inside and outside for a point mass. And then ring. For a ring also, there is no inside and outside point. Remember these field values, these gravitation field values, and you're golden. You can happily glide through this topic. You won't even have to face any other problem, in my opinion. Okay, just remembering all these hollow sphere, solid sphere values. Why don't you do one thing? Like if you are preparing your notes, prepare a note. I mean, like prepare a table for this thing. A point mass, field, a ring, field, a hollow sphere, inside field, outside field, a solid sphere, inside field and outside field. You do this, that's it. The values are so simple to get and you don't even have to put an effort into understanding this topic. Okay. Now, guys, today's topic is the most tedious topic I know because it has a lot of derivations. I understand this. I suggest you to watch it if you really want some good information about this class. And seriously, like today's summary, if you understand this thing, you are totally good to go for mains. For advanced, I can't guarantee. For advanced, you need to know the methods. It's good to understand that you I mean like it's good you don't. It's important that you need to understand these methods. Any doubts until this point? Aniket.
Sir, not doubt, just a request, sir.
Yeah.
Sir, all these videos, can you name them with the topics? It will be very easy when we are checking
I
again.
have a request to you. In fact, if you can name the topics that I've taught, I will definitely add those topics because there are too many topics in the past that I can't do it. I already heard somebody agree to do that. Somebody agreed to subtopic and give the, what do you say, like the video points. No, checkpoints. There's a new option in YouTube that you can actually put checkpoints in videos. If somebody is willing to do that, I'm more than happy if you tell me that. Timestamps, yeah, checkpoints, timestamps. If you can give me the timestamps. Okay.
Okay, sir, I'll do from now.
Yeah, please.
Okay,
At
sir.
least from
Sir, we'll
this
do
point
it.
onwards, do it now. Okay.
We'll just text it.
Yeah. Do it and text me and I'll add it. Chetan and Preetika, what are your doubts?
Sir,
Sir, in
once
examtracker.com, we can't access to gravitation day 1 video, sir. It's coming as it's not available.
I'll check. I'll look into it. Okay.
Yes, sir. Thank you, sir.
Chetan?
sir, I had understood that ring derivation, sir.
I can't understand. I can't hear you.
Sir, I not understood that ring one, sir.
You
Sir,
don't
he is
need it.
asking about the ring derivation, sir.
Like, please watch the video again, and even if you don't understand it, you can leave it. You can simply remember the formula. There is no problem at all. Try to watch the video again. Even if I explain it again, I'll just explain the same thing. I don't even change anything. Okay.
Oh, okay, sir, I watch.
Yeah. Guys, any doubts regarding the class? First of all, any doubts regarding the class?
No, sir.
No. Well,
No,
then
sir.
I'm stopping the recording. Okay.